Alright, so here you may need to print this off, and it should be sent to you in the email. I want to do it a little differently because this is a lot of writing, and it's nice to just go have everything already written out for us. So I'm just going to fill in the blanks. Hopefully I left myself enough room on some of these. So we'll just play that by ear. Alright, so first a blank, so a point estimate. A point estimate is the value of a statistic that estimates the value of a parameter. Alright? I know it doesn't mean a whole lot right now, but as you do some problems and you read back through this again, some of this will be a little clearer. Next, a blank, so a point estimate, we're saying that again here. For a population proportion is p hat, and that's equal to x over n. Alright, so basically we're given a scenario and we don't know much about it other than it has certain characteristics. That's what p hat equals x over n is telling us. We're telling it that we have a size of n and x of them have a characteristic that we want to look at. So it's either they have it or they don't. It's one or the other. So a point estimate is p hat, and this is how we're estimating a value. All right? So example 1, at ABC Company, 500 employees were surveyed and asked, are you currently on some form of low-carb diet? Of those surveyed, 75 said they were on low carb. Find the population proportion of individuals who surveyed who were on a low-carb diet. So this is a pretty straightforward one. We're finding a population proportion. All right, we don't know the whole population of the entire country, but we're looking at 500 that were surveyed. So p hat, since I'm dealing with a population proportion, all right, and the total that we're looking at is 500, and how many of them have that characteristic that we're looking for? 75. Either they're on a low-carb diet or they're not. So there's only two options there. All right, that's the answer here. And we'll start expanding on this some more. We're going to get into confidence intervals and how confident we are that this is the true population. And I guess I could have wrote this is 0.15%. All right, my line's kind of messed up when I printed here, so bear with me on this one. A blank, so a confidence interval. We're going to be talking about these a lot. A confidence interval for an unknown parameter consists of an interval of numbers based on a blank. So my line just kind of jumped down when I printed. A confidence interval for an unknown parameter consists of an interval of numbers based on a point estimate, what we just found. So what this is telling us is we're using a point estimate, and with this point estimate that we found, we can now create a confidence interval. All right, confidence interval estimates for the population proportion are of the form. All right, so this is just the general guideline of how to find a confidence interval. I'll get into the more detailed formula here in a minute. So it's the point estimate plus or minus the margin of error. All right, and to put those in simpler notation, point estimate we already know is p hat plus or minus the margin of error we label as E. So p hat plus or minus E. All right, next, the blank. So here, the level of confidence. The level of confidence. So I talked about level of confidence in the video about Z alpha over 2. So if you haven't watched that, please go back and watch that because we will be calculating Z alpha over 2 for the this whole section. The level of confidence represent the expected proportion of intervals that will contain the parameter if a large number of different samples is obtained. So that's important, a large number of different samples. So that we need a level of confidence because each sample will have a different mean and standard deviation. So we want to create this confidence interval using a level of confidence, and we'll get into more about what that means. So the level of confidence is denoted as, and this, I'm going to write it right here instead of on that line. It's 1 minus alpha times 100%. Meaning, if your level of confidence alpha is 0.05, you plug 0.05 in here and you get a 95% confidence interval, or level of confidence, excuse me. If alpha is 10%, 0.1, you plug it in here and that gets you 0.9, so that would be 90% level of confidence. So this is just kind of a concise way of identifying what alpha is, and we'll see some more of that here in a little while. All right, so example 2 down here. Suppose in example 1, it is known that the margin of error is 0.04. So that's E. And the level of confidence is 95%. All right. Find the confidence intervals and explain. All right. So, what does this tell us that alpha is here if it's 95%? That means, and I'm going to write it, just below. That means 1 minus 0.05 times 100%. That would be our level of confidence. That equals 95%. 1 minus 0.05 is 95%. All right, so what this is telling us, that implies alpha is equal to 0.05. All right, so just as a side note there, what we want to do now is calculate the point estimates. So let me get a different color here. And not the point estimates, we want to calculate the confidence interval. All right, so to calculate the confidence interval, we need to do this formula here. We need to say we have p hat plus or minus e. So we have two, with plus or minus, so there's two different formulas we need to work out here. We need to work out p hat plus e and p hat minus e. All right, one will be the lower bound, which is the minus, and one will be the upper bound, which is the plus. All right, it told us in the problem the margin of error is 0.04, so we know E is equal to 0.04. And now we can just plug in. P hat we found up here in the previous problem to be 0.15. So P hat is 0.15 plus E, which is 0.04. And that's equal to 0.19. And then same thing down here, except a minus. And that's 0.11. Okay, so that's our confidence interval. Now, explain. What this says is we are 95% confident. How do I know this? Because it tells me my level of confidence is 95%, or alpha is 0.05. So we are 95% confident the proportion who is on a diet, a low-carb diet, I'm just saying diet here, is between 0.11 and 0.19. All right, so here in a minute we're going to learn how to actually figure out what alpha is, and we're going to dig into this margin of error formula a little bit more. But in general, this is the end statement. This will be the last couple steps you would do in the longer steps, and we'll get to one of those problems in a minute. So we are 95% confident the proportion who is on a low-carb diet is between 0.11 and 0.19. All right, let's move on to the next page. So here, interpreting confidence intervals. All right, so here I'm going to actually write the formula out and then do a couple Z alpha over 2's for you. So we would say, and we may need a little room here, so I'm going to write with, I'm going to write conservatively here. The actual proportion P is within our confidence interval. I ran off the page here. The actual proportion is within our confidence interval. All right, so P is the actual proportion of the population. We're using P hat because we just have a small proportion of that population. But if we want to actually figure out P, we use P hat plus or minus E, the margin of error, what we just calculated. So what that's saying is, if we were to write it out, we could say P hat plus or minus E. That implies that P is between these two values. So you watch me for a second. That way you can kind of see what I'm doing here. So this formula implies that P hat minus Z alpha over 2 times the standard deviation of P hat, all right, is less than P, and that's less than P hat plus Z alpha over 2 times the standard deviation of P hat. So here, what this is saying is, if we want to know what P is, the actual proportion of the population, it will be between this value and this value here. So this is your margin of error, P hat minus E. E is Z alpha over 2 times the standard deviation of P hat. And that's the lower bound. The upper bound is P hat plus Z alpha over 2 times the standard deviation of P. So in the previous problem, I gave you what this portion was here, E. Now we actually are going to have to calculate Z alpha over 2 and calculate the standard deviation. All right, let's, so just as a refresher, and I'm not going to calculate these, but I'm going to give you a couple things called critical values, which are basically finding your Z alpha over 2. All right, go back and look at how I found Z alpha over 2 in the previous video. Here I'm just going to give you the numbers for just some, from the most commonly used levels of confidence. So I'm going to have a table here. Over here, let's have level of confidence. And you may want to pause and watch how big it is first. It's up to you. That's alpha. Here we want the area in each tail, which is alpha over 2. And lastly, this is the value we want, the critical value. The critical value is Z alpha over 2. So here, this is just telling you the area in each tail, like I showed you in the previous video. And the critical value is when we actually look that up into the table. All right, so when you look up the value in the Z table, this is the number on the outside edges. All right, and so if you have a 90% confidence interval, what does that tell you your alpha is? all right? You have to go back and remember we used the formula 1 minus alpha times 100%. That's not the answer. I'm just showing you the formula one time here. So what value of alpha do I need to plug in here so that I get 90%? That means this is equal to 0.1. So alpha is 0.1 there. All right, I'm going to finish these out real quick. 95%. What does that tell you alpha is? You have to plug it in here, and so you get 0.05. And 99% is 0.01. So basically, these add up to 100 or 1%. Excuse me, 100% or 1, however you want to view it. But we're using this formula to get there. All right? Now, what does this tell us about the area in each tail? Again, go back and look at the previous video for how I did that. I'll show you briefly. The alpha over 2 just means we take our alpha and divide it by 2. So in this first example, you get 0.1 divided by 2, which is 0.05. All right, and just finish the rest of these out. 0.025 and 0.005. All right, so that tells us how much area is in each tail. Now the critical part, or the important part, the critical value. This is the value that you will plug into this formula up here. All right, and so here at a level confidence of 90%, meaning alpha is 0.10 and alpha over 2 is 0.05, this is what we're concerned about, is the critical value of z over 2. Z alpha over 2 is 1.645. And here on 95% confidence interval, Z alpha over 2 critical value is 1.96. And here it's 2.575. All right, I encourage you to try to work these and find these yourself. I won't always give you easy values like these. All these values are on the bottom of your Z table, so that's also helpful to know and have. All right, keep going here. We're going to move on. So here is the actual formulas. It's going to be the same thing I wrote up here, except now I'm just going to write in the formula for the standard deviation of p hat. All right, so when you're calculating the margin of error, remember margin of error is equal to E. That is Z alpha over 2. You get that value by using either this table or actually calculating it yourself if it's not a common level of confidence. And then that's multiplied by the standard deviation of p hat, which was here, but now I'm going to actually plug in the formula for the standard deviation of p hat. So that's multiplied by the square root of p hat times 1 minus p hat all over n. And all of that is within the square root. So every time you work one of these, you're always going to have to find the margin of error, and that's how you find it right there. And now the lower bound and upper bound. We've already basically discussed these. But the lower bound, you start, I'm just going to say LB. All right, it's p hat minus E. All right, p hat we just leave as p hat. We know what E is. It's this formula here. It's Z alpha over 2 times the standard deviation of p hat. So p hat minus Z alpha over 2 times the square root of p hat times 1 minus p hat all over n. All right, and the upper bound is the same thing, except instead of a minus, it's a plus. All right, there's that. I'm going to go ahead and move on now. Now let's get into a problem where we work we work the whole thing in its entirety. All right, so as I go along, I will label steps 1 through 5, or 1 through 4, and then you'll get a good picture of what we're doing here. So this example 3 is basically combining everything we did on the first 2 pages. So example 3, 800 randomly selected drivers were asked if they ever use their cell phone to text while driving. 272 said yes. Obtain a 95% confidence interval for the proportion who text while driving. All right, so here you can clearly tell that we're going to have to use a proportion because we're given 800 randomly selected drivers and 272 of them have the characteristic that we're looking for. It's either a yes or a no. So yes, we're dealing with a proportion. All right, so step 1, find p hat. So p hat we said was equal to x over n. So here it's 272 over 800. And that is equal to 0.34. So 34% of these 800 randomly selected drivers said they text while driving. Step 2 is determine our critical values. So really what I'm doing here in step 2 is I'm starting to find the margin of error. Instead of just saying step 2, find the margin of error, I'm breaking the margin of error out into several steps. That will just help you along the way. And when we get to actually calculating it, you'll have everything you need to just plug in. So let's write that. Determine critical values. All right, or value, I should say. We only care about the positive here. All right, so to determine the critical value of Z alpha over 2. Now, we need to know our level of confidence, or our confidence interval. It says obtain a 95% confidence interval. So that tells us what alpha is. All right, what is alpha here? Alpha is, here this tells us alpha is 0.05. All right, so Z alpha over 2 would be Z of 0.025. I just plugged 0.05 in here and divided by 2. I skipped a step, so hopefully you're okay with that. And I'm just going to give you the answer here, but please be comfortable with how to calculate these on your own. It's 1.96, and I also gave that answer in the previous table that we just worked. All right, so there is Z alpha over 2. Step 3, find bounds. So I'm just abbreviating. This means find the lower and the upper bounds. So here we can start by finding the lower bound. LB is equal to, the formula is P hat minus the margin of error E, which is equal to, I'm just going to keep writing the formula out. It's important to know these. Z alpha over 2 times the square root of P hat 1 minus P hat all over N. And now it's plugging in everything that we know. And it may be easier to go down instead of over, so that way you don't miss something. So P hat is 0.34. We found that in step 1. Minus Z alpha over 2. which is 1.96. We found that in step 2. We can put that in parentheses if you like, just to show that we're multiplying. And then that's multiplied by this thing. So it is 0.34 times 1 minus 0.34 all over n, which is 800, and it's the square root of that. I find it easier to go ahead and write the inside first and then the square root, so that way you things just usually line up better for me doing it that way. Do this calculation and you get 0.307. And you'll do the same thing for the upper bound. I'm not going to work the whole thing out. It's p hat plus e, and when you work that out, you get 0.373. All right, I did not leave myself enough room here, but that's okay. Step 4, this is the last step, interpret. Interpret. All right. So I'm gonna block it off so I've got some room here. What this is saying is we are, actually I'm going to start up here. We are 95% confident that the proportion who text and drive is between 0.307 and 0.373. So what this is essentially saying is, so our p hat here was 0.34. For the 0.34 is only for these 800 randomly selected drivers. All right, that's not. I'm not telling you that of all the drivers, 34% text and drive. I'm saying 34% of just this 800 text and drive. What we're doing by finding this confidence interval is we're saying now we can say that of all those who drive, we are 95% confident that between these two numbers, that percentage of people text and drive. So if we did another sample of 800 people, we would be 95% confident that that proportion would lie between these two numbers. If we did a third sample of 800 randomly selected drivers, we would be 95% confident that that proportion would lie between these two numbers. So the 95% is saying that we expect 5% of those that actually, we expect 5% of the 800 randomly selected drivers of those samples might lie outside of here. All right, let's keep going here. So this bottom part, to find a sample size needed. So if you are working some real world problem, let's say, people texting and driving, and we're not sure what size of sample we need for this to be a valid experiment. This is how we can determine what size of sample we need. And this is part A. So to find a sample size needed, if p hat is a prior estimate of p, we can use this following formula I'm about to show you. Now the formula I'm going to show you is something you're already familiar with. It's the margin of error, but it's just algebraically manipulated to solve for n. All right, so in other words, it's taking just this margin of error, this z alpha over 2 times the square root of this whole thing. We're solving this for n, and so here's the formula though. It's n equals p hat times 1 minus p hat times then, and you may want to watch this before you do it, z alpha over 2 divided by e, the margin of error, squared. So this is just the margin of error algebraically manipulated to solve it for n. In part B, if there's a chance, and there's a chance that you don't have a p hat as a prior estimate, so if no prior estimate of p is available, we want to use this formula. N is equal to, so it's the same formula except this p hat times 1 minus p hat is gone now. Since we don't have a prior estimate, we can't use that anymore to our advantage. So just something we use, something simple, safe to use would be 25%. And then this stays the same. Z alpha over 2 divided by E, and all of that squared. All right, we are going to look at an example now of this. So what sample size should be obtained if you want to estimate within 2 percentage points of the true proportion with 90% confidence, if part A. So part A says a prior estimate of 10.7% is available. All right, so we have to figure out which formula we're using, and we know we're using a prior estimate. So that means we are using N is equal to P hat times 1 minus P hat times then Z alpha over 2 divided by E squared. All right, so we need to figure out what all these things are first. Before we just start plugging in, it'll be easier if we write them down. So let's start at the beginning. P hat, we need to know what P hat is. P hat, it tells us, is 10.7% or 0.107. All right, we know P hat, we know P hat. What is Z alpha over 2 here? I'll start it for you. Z alpha over 2 is equal to Z of 0.1 divided by 2, which is Z of 0.05. And remember, it's alpha over 2, so be comfortable with doing this. I know I keep saying that, but it's important. It's just a small little step that you can get the whole problem wrong. And this is a common one that I wrote down earlier. It's 1.645. And then the last thing we need to know is E. E, it's given to us. What sample size should be obtained if we want an estimate within 2 percentage points? That tells us E is 0.02. 2 percentage points means 2%. Move the decimal over twice, gets you 0.02. So now it's just plugging in that value here. So plugging all that in here, you get 0.107 times 1 minus 0.107, and then times 1.645 all over E, which is 0.02, and that's squared. So I didn't leave myself a lot of room here. So what I'm going to do is I'm going to come over here. So N is equal to 646.4. All right. Since we're dealing with, we don't want to deal with decimals here, because typically if we're dealing with people, which is typical, we're not going to have a 0.4 of a person. So we want to round up. So that implies N is equal to 647. All right, down here, where there's no prior estimate, we're at the formula. Only thing that changes is now we're using 25% instead of P hat times 1 minus P hat. And then I'll just go ahead and give you the answer here. N is equal to 1691.3. which implies we need a sample size of 1692. All right, that's it for now.